Professor Bob Young back at you, and we're going to continue our discussion of rational functions by finding the asymptotes of these functions here. So this is what we talked about in the last video. Now, to define asymptotes, if p of x and q of x define polynomials, for the rational function defined by f of x equals p of x over q of x written in lowest terms, and for real numbers a and b, one, if f of x, the absolute value of f of x or y, approaches infinity as x approaches some number a, then the line is called a vertical asymptote, or bah. And we'll get to this more. I mean, some of these definitions scare students and stuff, but hang in there. Two, as y approaches some number b, as the absolute value of x approaches infinity, then the line y equals b is a horizontal asymptote, or ha. So how to find them? How do you find these asymptotes? And really, these are the easiest way to sketch graphs of any of these functions, as we'll learn in the next video. To find the vertical asymptote, or va, simply find whatever number or numbers make the denominator equal 0. And whatever those number and numbers are, you just say x equals that as the va. Other asymptotes. To find the ha, all right, we're going to look at the degree of the top and bottom of each polynomial fraction. So it says if the numerator has a lower degree than the denominator, then there is a horizontal asymptote, y equals 0, the x-axis. So what they mean here, let's say if we have y equals x over x squared plus 1. Notice the power on x, the top degree is 1. That is the power on the variable x, while the bottom degree is 2. So that's what they mean by this. Whenever that happens, the ha, or the horizontal asymptote, is y equals 0. Other examples we looked at earlier, we looked at these two graphs, y equals 1 over x, and we also looked in the last video at y equals 1 over x squared. Now notice here, there is no x in the numerator of either one of these, and the denominator is 1 in the first one, the degree, and it's 2 in the second fraction there. So again, if you thought of this, you could put 1x to the 0 power there. The top degree is smaller than the bottom degree. In both of these, you could put x to the 0 power there. Of course, that's the number 1, the ha, y equals 0, whenever the top degree is smaller than the bottom. Now, the other type of asymptotes we're going to talk about, we haven't considered this one yet, is what if the degrees are the same, Young? What if the top degree is the same as the bottom degree? And then you've got these giant polynomials here. So you might have something like y equals 2x squared minus 7 on top, and 3x squared plus 4x minus 1. I know some of you are going, Young, you're scaring me. Now, to get the ha on this one, when those degrees are the same, you just look at the coefficients in front of those degrees with the same power. So that's what they're saying here by this a to the n over b to the n. If those degrees are the same, it's just the numbers in front that would give you the ha. Y would be 2/3. All right, let's take one more and see if y'all have it. What if I gave y'all, and I'll do green up here, y equals 2x minus 3 over x plus 1, which we may graph something like that in a little bit. Now notice both of these degrees, exponents on the x's are both 1s, so it's those numbers in front that then determine the ha. So it would be, in this case, y equals 2 over 1, or y would be 2. So again, if the top power is smaller than the bottom, y equals 0. If they're the same, it's the coefficients in front that you determine the ha. And there's one more case. If you have the numerator is exactly 1 more than the denominator, 1 degree higher, then we have what's called, there is no ha, but there's something that's called an oblique asymptote. Now, I don't really like oblique. I like this word slanted asymptote better. So Young says when the top degree is exactly one more than the bottom, you're going to have what's called, I'm going to abbreviate it, the SAW. And we're going to show you how to find those as well as we do some examples here. So I know what y'all are saying, Young, you better have some handout in the care package that's going to help us, or an angel that's going to help us, and I do. And here's what it looks like. It's actually just one page, but I had to break it up here and doing the video, so I broke it up. It's called Graphing Rational Functions. And it tells you, given these polynomial functions here, P of X over Q of X, it does go through very nicely how to find the VA, just whatever numbers make the denominator 0. So Young tried to put all this stuff we've been going over in plain English for you. Now also I said how to find the HA, and notice I tried to make this a little bit easier for you here. I said if the top degree is less than the bottom degree, then it's Y equals 0. If the top degree equals the bottom degree, and I gave you an example over here, it's those coefficients in front that give you the HA. And if the top degree is greater, there is no HA. But there may be, as we'll see in this next slide, a SA, or oblique asymptote. So here's an example here. Now, how to find the slant asymptote of it has it when the top degree is exactly one more than the bottom. And notice here I said to find it, use long division and divide the bottom into the top, disregarding the remainder. So I just took this x plus 1 here, and I divided it into x squared plus 3x plus 5. All right, and if you want to, I think I'll include a video on how to long divide things in case y'all forgotten how to long divide. And it doesn't look like the lines came through here, but we throw out this remainder of 3, so we get the top part there, y equals x plus 2, as a slant asymptote. So I'll have to remind myself here, make a note to put the long division notes in there if you want to figure, if you've forgotten how to long divide. Now let's say a note here. Let's take a breath. The graph of a rational function may have more than one vertical asymptote, or it may have none at all. There might be more than one number that makes the denominator 0, or none. The graph cannot ever intersect any vertical asymptote. Okay, there can be at most one other non-vertical asymptote, a HA or SA, and the graph may intersect that asymptote, as we shall see in the following examples. All right, now let's look at this function here, and notice it's saying we're finding the asymptotes here. So if we look at this one, we could take the denominator and set it equal to 0, and we will get more than one VA here. So we could say the VA, this would be in this case plural, the vertical asymptotes are VA, x could be equal to 1/2 or x could be equal to -3 in this example. All right, so now what if we want to, it says to find the equation of the HA, divide each term by the greatest power of x in the expression. Now before we go doing this, I like just looking at this thing we've already talked about here. Now, they're going to show you why this is true, okay? But we've got x to the first power, and this is really what we're concerned with, is the top dogs, over 2x squared. Now, since the top is smaller than the bottom, we already know by Young's handout that y equals 0 will be the HA. Now, we're going to show you why that's true. They're going to divide everything, and this is going to maybe spaz you out. They're going to divide each term in the numerator and denominator by x squared, since 2 is the greatest power of x in any of those things we looked at. Now, notice when they do that, what happens? This becomes 1 over x plus 1 over x squared. X over x squared reduces to 1 over x. This reduces to 5 over x minus 3x squared. Now, it says stop here, leaving it in this form, which kind of looks yucky. I know they're saying, why would you do that, Young? Now, notice what they're trying to show you here. As x gets larger and larger and larger, the quotients of all of those things which we divided there approaches 0. So if you think about it, 1/10, 1/100th, 1/1000th, 1/1,000,000th, those are all going to go to 0. And what are we left with is this fraction 0/2. And that's how they show, like in calculus and pre-calculus, that the horizontal asymptote is 0. All right, now let's go ahead in the second example. We'll find how to get the asymptotes here. Now, in this one, since the denominator is x minus 3, 3 will make that denominator 0. So I would say right away, we could almost look at this one and do the va and ha. These are the kind I like. These are the kind I like to give on tests. So the va would be what number or numbers make the denominator 0, 3. And of course, you could take that denominator and set it equal to 0 and solve if you didn't see that. But this one I think most people could see. To get the horizontal asymptote, notice the degrees of the x's are the same. So do you remember what that means? Well, it means these numbers in front of the x's will give you the horizontal asymptote, or the ha. So it would be y equals 2 on this one. Now, they're doing their funky thing again. They're dividing each part of this fraction by the highest powered x, which in this case is 1, showing you that you could rewrite this thing in this really ugly looking manner, which some of you may or may not like. But do you see, as x gets larger and larger and larger, these are going to go to 0, and you're going to be left with the fraction 2/1. Now, you can forget about the 1 on top of the x and the 3, because as they go in the millions and stuff, they're going to go out of sight. And that's what they're saying here. You will get it to be y equals 2. So you could either look at the degrees of the top or bottom, as you do a lot of these, to figure out what the ha is, or you can divide by the highest powered exponent. Okay, now we got one more example here. Now notice again, the va on this one would be 2, because 2 would make the denominator 0, and we could set it equal there to 0. Notice on this one there is no ha, because the top power is greater than the bottom power. So it looks like it's going to be long division time. So we could take and long divide this, and they're going to show synthetic division here in a minute. Those of you that remember how to synthetically divide, you can do this one by synthetic division, but long division always works. So I'm going to go ahead and take the bottom end of the top and include that x to the first power term there so things line up. So when you long divide, and I'll put a video in there to refresh your memories on how to do that, you take first term into first term, x goes into x squared, x times. Multiply, you'll get x times x minus 2 is x squared minus 2x, which gets subtracted from what's up there. So draw the line, boldly change the sign, subtract. The x squares go out, you're left with 2x plus 1 here. Then you just repeat. X goes into 2x plus 2 times. That'll give us 2x minus 4. Now we can throw out the remainder, so we can now say y would equal x plus 2. And we might show you one more way to accomplish this here. We could divide every single term by the highest powered x squared here. All right. Now notice here, if we're trying to find the ha, we get 1 over 0, because as x gets extremely large here, y goes to, it's going to be undefined, so we know we don't have a ha, so we have to get a va. So here's how to do it using synthetic division. We're just going to go ahead and synthetically divide. And remember, synthetic division, you can take 2, and then you can break up the coefficients of the polynomial into 1, 0, 1, and you will still end up with y equals x plus 2, and you can throw out the remainder there. So I don't really want to get into too many different things on long division versus synthetic division and stuff, but if you folks remember how to synthetically divide from your previous courses or high school, when you can, do that. But like I said, long division always works. So for very large values of x, 5 over x minus 2 is close to 0, and the graph approaches the line y equals x plus 2, which is called an oblique or slant asymptote. for the graph of a function, and we will look at getting into the graphing part next, now that we've got some background into the basic graphs and how to get asymptotes. We're all set for graphing rational function action in the last of the 3 videos. Professor Bob Young signing off. Until next time.